Okay, the last problem that most people had an issue with, and it's extremely understandable because it's a difficult problem, okay, is number nine. And that one, you have a person standing on the edge of a merry-go-round. They give you the mass of the person at 60 kilograms, the mass of the merry-go-round at 100 kilograms, and they give you the initial angular velocity of 2 radians per second. Okay, those are your initial conditions. Now, obviously, the mass of these things is not going to change. Okay, so your final condition, those masses are still the same. What happens at the end, though, is that this person has walked inwards, right? And they end up only zero point 0.5 meters away from the center of rotation at the end, whereas at the beginning they were on the edge, so they were 2 meters away, okay? The disk, again, didn't change. The merry-go-round didn't suddenly explode or implode, right? It still has a radius of 2 meters. So that didn't change. The only thing that changes from the initial to the final condition is where the person is standing. They were on the edge. Now they're only half of a meter from the edge. So what we have to do is realize the axis of rotation still did not change. Okay, so the thing that is still true is that our angular momentum is still the same. Okay, our angular momentum is still conserved. So the other bit of information you have to know, and you have to look this up off those tables I gave you, the moment of inertia for a disk is 1/2 mass times radius squared. Okay, and the moment of inertia for a weight on the end of a string. So basically just kind of something that you're flinging around in a circle, like this guy right here should work. So if I have a weight on a string, imagine there's no mass whatsoever to the string, all the weight is in this carabiner. The only thing you have to worry about is just the mass on the end of it, and that moment of inertia for that thing is just mr squared. It's the simplest moment of inertia you can get, okay? And that's what this guy is. He's just a weight that's being flung around on top of a disk, okay? So that is his moment of inertia. Here's the moment of inertia for the disk. They're both there. They both exist. They're both on top of each other. So you have to still include both of those things in your angular momentum calculation, okay? So if you remember your angular momentum, that formula for any angular momentum, final, initial, whatever, is I omega. Okay, so our angular momentum is the same on both the initial and the final condition because nothing is being done to this disk. There's no outside force acting on the thing, and we're not changing the center of rotation. Okay, we're not moving that spin axis, so our angular momentum is conserved. Okay, so because of that, here's what we need to do. This is really easy. This is simple. We can do this one, but can you do it when you have two different objects? Yes. What you need to know is this is I total. So how do we find our I total? You got to add them up. If you got more than one, you have to add them all together. Okay. So for this, what you're going to have is for both the initial and the final condition, you're going to have the moment of inertia for the disk plus the moment of inertia for the person, for the weight, I guess I called it earlier, right? He's a weight on the end of a string, basically, or a weight going around in a circle, right? So the sum of those times your omega, okay? So we need to find this value for the beginning, and then we need to find it for the end. Okay, so our I of our disk, we got to break this down even further because we need to put this in place of our I, right? So our formula becomes a little more complicated. Instead of I of disk, I'm going to put 1/2 mass, okay, and our mass does not change, is 100 kilograms, okay, and our radius of our merry-go-round also doesn't change, okay? So this is r squared, so 2 squared, okay, plus the I of the person, okay? So mass of the person is 60 kilograms. That doesn't change. But what about the radius of the person? Does that change? Well, he started out 2 meters out, and then he walks in until he's only half a meter away. So that's the thing that changes, okay? So I'll just put r squared here, okay? And times your omega. So that's the formula we got to work with. And here's the thing that changes. This changes. This number is constant. So if this changes, that's constant. Everything else in there is constant. That also has to change. Okay, how do we solve this? We have one formula with, well, 1, 2, 3 unknowns. Actually, this isn't an unknown. We know that number, right? But we got 1, 2 unknowns. You can't solve a problem with 2 unknowns, can you? So you've got to be able to put something else in there to figure this one out, okay? So here's what we do. What we're going to do, and actually, I'm an idiot. What am I doing? I'm an idiot. For the first one, we actually do know our omega, so the only unknown that we've got is just this guy right here, okay? Forget. All right, so L initial. And I'm going to go ahead and erase some of this, okay? We need to find, don't forget before I erase this, the thing that we need to find is our omega final. Okay, that's what we're looking for, our final angular velocity. Okay, so let me create some room for myself here, okay? So, we know for our initial, okay, L initial has to be equal to L final. So I'm going to turn this, I'm going to plug in all the values for our initial condition. Okay, 1/2 times 100 times 2 times 2, 2 squared is 4, okay, plus 60. Now, his radius to begin with was 2, okay, so 2 squared, or 4, right? And then that, the sum of those things, times our omega initial, and that was 2, okay? So that right there is our L, our initial angular momentum, okay? Now that has to be equal to our final angular momentum, okay? So I'm going to go ahead and erase this one. Well, actually I'm going to leave it up here. I'm going to cram something in and then I'm going to erase it later on, okay? So L initial has to be equal to L final. So let's use this again to find our L final. Again, nothing in our I value changes from our initial to our final for the merry-go-round. It's still the same, okay? So we still have 1/2 times 100 times 2 squared, so times 4, okay? Plus, guy's mass didn't change, okay? But his radius did. So his radius went to times 0.5 squared will be 0.25, okay? So that's our I value for a final condition, and we want to know, the thing we want to know is our omega final. So now look at it. We have L initial is equal to L final, okay? We have all the values we need for the initial condition. We have all but one for the final condition. So now we can definitely solve this formula, okay? So if I do that, I'll get 50 times 4, 200, and then 60 times 4 would be 240. Yep, okay. Times 2, okay, is equal to, again, 200 didn't change, plus 60 times a quarter, though. That's a big change, isn't it? Okay, so a quarter of 60, which would be 15. Okay, so that is times our omega final. So now if I solve this out, simplify this down and this one down, I'll get 200 plus 240. Okay, so I get 440. 440 times 2 is equal to 215, 200 plus 15, right, times our omega final. All right, so I'll get 880 here. Okay, so let me bring this over here. So all this simplifies down to 880, 440 times 2, okay, 880 is equal to 215 times omega final. So if we want to find omega final, what does this take and divide 880 by 215? And that is our omega final. Plug it in and you got it done. Now, not too bad. The only tricky part to this entire problem, there was a lot of steps, there's a lot of stuff to put in, but the only thing that's really tricky, other than just number crunching and keeping track of all your numbers, the only thing that was tricky is realizing that instead of an I here, you have a sum of your I's, okay? Your total moment of inertia is just the addition of all your moment of inertias together, and that's it, okay?